Right, so in calculus, we use limit notation a lot. Many pre-calculus courses also kind of delve into limit notation. So hopefully you've seen this notation. If not, obviously just let me know in like one of the first few classes. So if we want to represent some of this end behavior in limit notation, we could do it this way. So just in case it's been a while, you've never seen it before. So this down here gives us information about the domain of the function, right? So this is saying as x approaches negative infinity. Right, so if I kind of looked at just my graph for a second. So I'm thinking about what happens as I go off this way from my function, right? And go off that way a lot, right? We're going off towards negative infinity. This right here, right? So whatever this is usually going to be our function, right? So this is f of x, right? So remember, this tells us something about the range of the function, the y values. So this notation is saying, as our values of x, as our input values get really, really kind of like big in the negative direction, what do our y values start to do? So if I have x to some even function, right? So I know an even function looks like this. So as x goes off in this, gets big in the negative direction, our function is doing this, right? It's going that way. So what y values are those approaching? Well, they're just getting bigger and bigger and bigger and bigger and bigger. They're approaching infinity. So if we did the same thing, if I said, well, what happens as x goes off in the positive direction? That arrow wasn't as nice, right? So here, well, my function is still approaching positive infinity, right? As I plug in a bigger and bigger value of x, and then I raise that big value of x to an even number, it's just going to go off towards infinity as well, right? So this would be kind of like the end behavior limit notation of what these functions do as x goes off towards a positive or a negative infinity, right? So if we look at this from an odd perspective, right? So I have some odd function, doesn't matter if it's x to the first power or x to something different. I'll use x to like some odd number greater than 1. We know our functions look like this. Right, so as I go off in the negative direction, right, what is my function doing? Well, it's going down, right? It's decreasing, but it's decreasing without any real kind of bounds or limits, right? It's getting smaller and smaller and smaller. Right? So this is approaching negative infinity. And by that same token, if x gets really, really large in the positive direction, it goes off towards infinity. My function is also getting bigger. We're approaching infinity. Right, so there is a little technical note here. So you can read the technical note. Basically, like to be precise, we shouldn't ever say that this limit equals infinity, although a lot of times, if you've taken kind of a calculus before, your teacher may get lazy and write equals infinity. I'm sure I will write it that way as well. But since infinity isn't a number, we can't actually ever equal it. This is why we kind of like write this arrow to say it's approaching infinity. It can get as bigger and bigger and bigger and bigger and bigger. It's increasing without bound. And this is something we'll explore a little bit later on when we talk about the actual definition of a limit. All right, so then a couple of other things about end behavior that are important. So we have these parent functions, and these parent functions for polynomials look like this. But as we saw with kind of factored form, we can have some value out front as lead coefficient, and that can affect what the function does. So if we have some function, right? So this is just something that I kind of talked about on the other page, right? So this fancy z means the integers, right? Whole numbers, positive and negative. The positive means that I just care about like the positive ones. So if I have a times x raised to the nth power, where a is just some number, this a value does two things for us. Number one, it acts as a vertical stretch. And so we saw that if a was bigger than 1, it means we're going to get narrower. If a is between 0 and 1, we're going to get wider. So notice that if I make my function wider or narrower, none of these things are going to change their end behavior, right? If I say I'm going to multiply this by 7,000, right, it's just going to kind of increase faster. It's still going to go off towards infinity in both as x gets like bigger in the negative direction and also bigger in the positive direction, right? So that kind of number, like the pure number, what we say the absolute value of a, doesn't affect the function at all. However, the other thing that a did, if a is negative, if a is less than 0, it functions as a vertical reflection. this will affect the end behavior of the function, right? So if I have some function that looks like this, right? So if I just have, for example, f of x equals x squared, right, we're going to look like this. But then if I say maybe g of x, just to be kind of precise and kind of use a different function, equals negative x squared, we're going to look like this. All right, so notice what happened, right? Since I vertically reflected my function, I'm changing my end behavior. We're not approaching infinity anymore. We're approaching negative infinity this time, right? So if a is less than 0, your end behavior flips. All right, so I'm going to pause for a second and do these examples just in another one, just because, hey, there's a lot of them. I would always recommend like trying these things on your own and just seeing what you get.